Okay, so we were talking about applications of Tutte polynomials last time. And then I showed you how to compute Tutte polynomials using this finite field method. Today I'm going to talk about another application of matroids and error correcting codes. Sorry, an application of matroids and Tutte polynomials to the subject of error correcting codes. So it's an application of matroids and Tutte polynomials to the subject of error correcting codes. Okay. What is the subject of error correcting codes? It's a very important subject, which I'm assuming is pretty close to frame theory. Is that reasonable?
Part of it, yeah.
So what's the idea here? The idea is that you have a message that you want to transmit from somewhere to somewhere else, but there might be errors in between. Okay, so you can think of it as for example, modems do this. You have a message that is going from one end through whatever system to the other end, but in between there's a lot of places where errors can take place, and so the subject of error correcting codes basically says, how do you encode information so that a noisy channel that might ruin your message will actually not ruin it. So maybe you want to transmit a message, and you want to transmit it in a way that even if there's noise in between, and even if the message gets jumbled up a little bit, you can still read it. Okay? And that's the subject of error correcting codes. So I mean, this is really applied everywhere. Modems do this. Cell phones do this. Credit cards do this. CDs do this. Let me give you a very simple example, which is the example of what credit cards do. So it might have happened to you if you were buying something on the internet that they asked for your information, and they ask for your credit card number, and you type in your credit card number, and you press send, and sometimes they'll just tell you immediately that's not your credit card number. And you might think that there's a lot of credit card numbers, and it's not so easy to look through the list of all possible credit card numbers and see if that's the right one. But the thing is that credit cards have a number, very long number. And some of these numbers are designed for correcting errors, because they know that people are going to type up their credit card and they might make a mistake. And so one thing you could do, for example, if this was a credit card number, you might just make the last digit be the sum of the other ones. So, this is A, this is B, this is C, and so on. Then this could just be the sum mod 10. So if this is how a company assigns credit card numbers, and if you happen to type a mistake and put a 3 instead of a 4 here, then the credit card, then whatever, it's very simple to check the last digit and see right away that there is a mistake. And credit cards have, I think, 2 or 3 digits that just do this, and they don't tell you how to do it because they want to prevent fraud. But basically, they have these last digits that kind of check and correct for any errors that you might have made. Okay. So what's the idea here? What is a code? A code is going to be a set of words. Okay. It's going to be a set of, actually I'm going to call it C for code. of words of length n in an alphabet S. Okay. And you know that, for example, for computers, the alphabet is 0 and 1. And so a word is just a collection of zeros and ones. So very often, the alphabet is just zeros and ones. Okay. And these are called binary codes. And for us, it'll be useful to pick a finite alphabet. And what we're going to want to use is an alphabet which is a finite field. And this is an example of one, because 0, 1 is the field of 2 elements. And we're going to do this for any field. Okay. Now, what is a good vocabulary? I mean, you want to pick a bunch of words. What is a good vocabulary for these purposes? Well, I think that a nice property of any real language that we use is that languages tend not to have too many words that are too close to each other. So that, I mean, this is of course a desirable property. If you don't want words that are so close to each other that maybe you misheard and you don't know which one of the two words it is. So if you happen to come up with a code where all the words are very different from each other, then it's easier to make mistakes. It's harder to make mistakes. And if there is a mistake, it's easier to correct it. Okay? And so the idea is that you want your code to consist of very different words. Very different words. Okay. What do we mean by very different? Well, one simple notion of very different is just defining a distance between two words. So if x and y are words, then the distance between them is just going to be the number of positions in the word where they disagree. And one thing that I want to emphasize is that all these words have the same length. Okay? So you're just going to compare letter by letter, and you're going to see how many positions they disagree in. Number of positions where x and y disagree. Where the ith coordinate of x and the ith coordinate of y are different. And I'll leave it as an easy exercise for you guys to check that this actually is a distance function, so that it does satisfy what you want a distance to satisfy, the triangle inequality. And so when we say that we want words to be very different, what we mean is that we want them to be far apart from each other in this, according to this distance function. Okay? And so the number that we care about here is the distance of the code. Is just the smallest distance between two words. The minimum distance between x and y for x and y in C distinct. Okay? And so we want it to be large. We don't want to use words that are close to each other. Okay? Okay. So now I'm going to show you a very nice kind of code, which is the one that people often use. People often use linear codes. And what is a linear code? Well, we basically have all these words of length n over a finite field. So our vocabulary, our code C, is a subset of fq to the n. And so a very natural subset of fq to the n is a subspace. Normally we're willing to call any subset a code, but it's going to be easier if we make our code be a subspace. So a code is linear if it's just a subspace of fq to the n. And the nice thing about them is this. Let's say that you want to compute the distance between x and y, two arbitrary words in your code. Well, of course, the ith coordinate of x and the ith coordinate of y agree if and only if the ith coordinate of x minus y is 0. Right? So the ith coordinate of x equals the ith coordinate of y if and only if the ith coordinate of x minus y is 0. Okay? So I'm not really saying much there, but then the nice property of linear codes is, first of all, that x minus y makes sense here. Now, really, it would make sense for any x and y in fq to the n, but the nice additional property is that if x and y are in the code, then x minus y is also in the code, because this is a subspace. And that's the nice thing. This guy is in the code. Okay. And so therefore, the distance of the code equals the minimum distance. Basically, the point is that you can assume y is 0 here and just compute the minimum distance between some word in the code and 0. Where 0, of course, is just the 0, 0, 0 vector. Okay.
Does that give you a norm on those guys? Or is that not a norm?
Yeah, yeah. Now, what's the distance between x and 0? The distance between x and 0 is just the number of non-zero coordinates. So it's the minimum size of what is called the weight of the word. And the weight of the word is just the number of non-zero coordinates. So the weight of a word is the size of the support. In other words, number of non-zero coordinates. Okay. So let me make this concrete. Let's say that, for example, you managed to find, say you found a code C of distance say 11. Okay. So that means that any two words are a distance 11 or more from each other. They disagree in at least 11 coordinates. Well, basically, what you can do now is you can guarantee that if you're, or maybe I should do it the other way around. So let's say that you're trying to say you wish to transmit a message So you basically you input a word, and then the word is gonna go through some noisy channel that might break it a little bit. But let's say that your channel will introduce at most 5 mistakes. Okay. So you somehow researched how this channel introduces errors, and you found that it's going to introduce at most 5 of them. The point is, now what you want to do is, if you manage to find a code of distance 11, then you're going to be all set. If you use a code of distance 11, then you're not going to have a problem, because here's the word, here's the real word. Okay, then it goes through the noisy channel, and you have at most 5 errors. And so in the end, this is the word, the incorrect word that comes out at the other end of the channel. But the point is that the difference between the real word and the incorrect word is at most 5 positions. Okay? And what I claim is that if you just look at this incorrect word, there is only one real word that it could have come from, because there is no other real word within 5 errors of this one. Because if there was, if the distance between this real word and this incorrect word was less than 5, and the distance between this real word and the incorrect word is at most 5, then that would make the distance between this real word and this real word at most 10. But these words are in our code, and we know that the words in the code are distance at least 11. Okay. And so what that means is that if you're able to put a bound on how many errors you're going to make, then that tells you what codes you should use, and you will be able to recover the information completely. You can recover the message perfectly. Okay. So this is basically the notion of an error correcting code. If you choose words that are far apart from each other, you don't have a problem. And of course, if the same argument tells you that if you can guarantee at most the errors in the transmission, then what you want is a code at distance 2d plus 1. Okay. So how do you actually do this? Let me just give you a toy example that's a little bit more concrete. This is a little bit of the philosophy of error correcting codes. But let's say that you want to transmit a very simple message, and your simple message consists of 2 coordinates, and each coordinate is 0 or 1. Okay? So the message that you would like to transmit is just zero or 1, 0 or 1. Okay? Well, the point is this one. If you if you just plug in the message 1, 0 and you send it through the channel, the other person might receive 1, 1, and how are they going to know? Was there a mistake in the way? Is this the right message? How do you know? The point is you don't want to just transmit A, B because that there might be some loss of information there. So what you want to do is maybe transmit a little bit of extra information that will allow you to detect a mistake. So what you might want to do is instead you're going to send A, B, A plus B. Okay. What is this going to accomplish? Well, and again, this is a toy example. Let me assume that at most one error is introduced. Okay. So if I sent 1, 0, then you're going to receive either 1, 0, 1, 1, or 0, 0. So either you get the correct message or one of the bits is flipped. Okay. So instead, let's say that I send A, B, A plus B. What am I going to accomplish with this? Let's say that my real message I'll ask you guys. So I give you 0, 1, 0. You know, I put something in my channel. This is me, and this is the noisy channel. Noisy channel. And then you're going to get 3 coordinates. Something, something, something. Okay? And I put something, something, something. Well, if you get 0, 1, 0, then what can you tell me? You can tell me there was a mistake. And why? Because this is not A plus B. So there was a mistake. What if I give you 1, 1, 0, 0? Well, there might or might not be a mistake. What do you think?
There's not, right? Because you only know there's at most one mistake.
There's no mistake, and the reason is this one, that I assume that at most one error was introduced.
Yeah.
And if one error was introduced, then it would just flip one of the things. Okay. But if this plus this is equal to this, you could only achieve that by making 2 errors. Okay. So there was no error here. No error. Okay. And so even by doing this very simple thing, you have a procedure where you can receive the message and either look at it and say, oh yeah, this adds up to this one, so this is what he meant to say. Or if it doesn't add up, then you can call me and say, hey, I got it wrong, send it again. Yeah? So just by this very simple check, you can accomplish that. What is the code here? Well, basically, let's think about this code in several different ways. So first of all, first of all, I'll ask you, how many words are in this code?
4.
4? Why 4?
0, 0, 0, 1, 1, 0, 1, 1.
Basically, what happens is that the first 2 coordinates determine the third one. So if you have 0, 0, then the third one is 0. If you have 0, 1, the next one is 1. If you have 1, 0, the last one is 1. And if you have 1, 1, the last one is 0. So that's the code. Those are the possible words in my vocabulary. These are the only 4 messages that I could send to you. Is this a linear code? It might not be obvious to you. First of all, where does this live? It lives in F2 cubed. Okay? And remember, you can think of this as a little cubic array. 0, 0, 0, 1, 1, 1. You can think of it as a cubic array. Okay? If this was a subspace, then what would be its dimension?
2.
It would have to be 2 because it consists of 4 guys,
Yeah.
and a subspace with 4 guys has to have dimension 2.
Yeah.
Okay? So if this is a linear code, then you can describe it in one of 2 ways. You can either give me generators, and you would have to give me 2 generators, or you could give me an equation that says it's this hyperplane, because a 2-dimensional thing in 3 dimensions is a plane. So either you give me the one equation that these guys satisfy, or you give me the 2 generators. So what do you think?
Hyperplane.
I mean, you can do it in both ways. So which one is easier?
Neither one's that hard in this
I think either one is all right. So for example, what are generators?
Any 2 of the non-zero ones, right?
You better not choose this one as a generator, right?
Yeah.
But for example, this one and this one generate this one. Why is that? Because if you add up 0, 1, 1 and 1, 0, 1, you get 1, 1, 0. So one way of presenting this is as the space generated by 0, 1, 1. Get rid of all these commas so we don't get lost with all the commas. So A times 0, 1, 1 plus B times 1, 0, 1. A, B, and F2. Okay, so that those guys generate, that's fine. Or you could also represent it as the points x, comma, y, comma, z that satisfy an equation. And what is that equation?
X plus y plus z equals 0.
You can write it in different ways. For example, you could tell me that z is x plus y. This is just the definition. Or since we're mod 2, that's the same thing as saying x plus y plus z is equal to 0. The point being that this is a linear code. That can detect one mistake. Can it fix it? If there's no mistake, then you guys know that there's no mistake, and that's fine, and you have the message. If there is a mistake, like in this case, you cannot tell what the mistake was. Because I could have sent you 1, 1, 0, which is one mistake away, or I could have sent you 0, 0, 0, which is one mistake away. So it can detect a mistake, but it cannot fix it. You'd have to just call me again and say, hey, send that again, I didn't get it. Okay. But, okay. What's the distance of this code? Well, we said for linear codes, the distance is the smallest support. So what is the word that has fewest non-zero coordinates other than the 0 word? Well, they all have 2 non-zero coordinates. So the distance is 2. Any two words in this alphabet, in this code, are at least 2 positions away from each other. Okay. And so, of course, we care about distance, and we saw that for linear codes, distance is basically the same thing as support, or weight is what I call it. And so what people associate to a code is the weight enumerator. The weight enumerator of the code is basically you're going to take all the words in your code And for each one of them, you're going to say the weight. So you're going to take t to the weight of the word. And so, of course, this is a function of t. And actually, people like to use a z here. So we're going to use a z. So this is a function of z depending on your code u. Okay. So for example, for this guy, what is the weight enumerator for this guy? Well, you're going to go through all the words of the code, and for each one of them, you're going to tell me how many non-zero coordinates there are. This one has no non-zero coordinates, so you get z to the 0. This one has two non-zero coordinates, so you get z squared, another z squared, another z squared. How can you read off the distance from here? Well, you're always going to have a z to the 0, which corresponds to the 0 word. This is a subspace, and so the 0 word is always in there. And it's the only word that has all coordinates equal to 0. And after that, the following term, the one with the smallest z degree, is going to be the distance. And so you can immediately read off the distance if you have this polynomial. And this polynomial is extremely useful. So people in coding theory want to know, here's a decoding algorithm. Is my decoding algorithm going to succeed? There's a certain probability of it succeeding or failing. And that probability can be expressed in terms of this weight enumerator. And so this is really the invariant that people want to compute for the weight for the code. So what's the theorem here? The theorem says that if you take a linear code, let U be a linear code in FQ to the n. And say that it's a dimension k linear code. Okay. Now, again, linear code just means subspace. So really what we have here is a subspace of FQ to the n. And this is a matroid theory class, right? And we saw that if you have a subspace, then that defines a matroid for you. So let M be the matroid of that subspace. And I'll remind you in a second what that matroid is. But if you take a linear code and you consider the matroid, then you can probably imagine the punchline. This polynomial that we care about is again just obtained immediately if we have the top polynomial of the matroid. And as usual, the formula is a little bit messy, but we know exactly how it should look. We should have something to the something, something to the something, and then top polynomial evaluated at the function of the co-loop, the function of the loop. And what you get is 1 plus cube minus 1 z over 1 minus z, comma 1 over z. In other words, the problem of computing weight enumerators is a sub-problem of the problem of computing top polynomials. Maybe what we should do now is let me prove this for you guys. Again, remember that when you have a statement about top polynomials, there's two proofs that you can look for. The first proof is just a recursive proof that says that this guy is a Todd-Grothendieck invariant. So that it just satisfies the deletion contraction recursion. If you do that, you're going to get this result. Or you can look for a more direct proof. And both work, and I'm going to show you a more direct proof. Okay? So to do that, let's remind ourselves of what this matroid is. So U is a subspace. And so remember that we said M was defined like this. We said that if you let this subspace be just the row space of some matrix, then the matroid M is the matroid on the columns. Linear matroid on the columns of A. And we said that, of course, different matrices can give the same row space, but all of those matrices have the same matroid. This is what you proved in the first homework problem of homework 1. Okay? And so let's just do this for that example over there, and then we'll see how this goes. U is the row space of those two guys that we chose. 0, 1, 1, and 1, 0, 1. Okay? So we can think of this matroid as being the matroid of a vector configuration. And the vector configuration consists of the columns. 0, 1, 1, 0, and 1, 1. Okay? So maybe I'll try to draw some pictures. Here we have some two-dimensional space in a two-dimensional subspace of a three-dimensional space, and so this just looks like some plane here. Here we have a vector configuration in the plane. Consisting of 0, 1, which is this one, 1, 0, which is this one, and 1, 1, which is this one. Maybe I'll call these V1, V2, and V3. So this is V1, well, 1, 2, 3. Okay. And we said that there was a third way of thinking about linear matroids, which was to talk about a hyperplane arrangement. And the hyperplane arrangement has one hyperplane perpendicular to each one of these guys. Okay? So the hyperplane orthogonal to vector 1 is this guy right here, 1. The hyperplane orthogonal to 2 is this guy right here, 2. And the hyperplane orthogonal to 3 is this guy over here. So this is the arrangement consisting of the hyperplanes y equals 0, x equals 0, and x plus y equals 0. Okay. This is hyperplane 1, hyperplane 2, hyperplane 3. Okay. So now that we have that, let's look at this weight enumerator. So what you want to do is for each word, you want to find its support. Okay. So for each word over here, let's call this U. You want to find the weight. Okay. So let's call this word, since it's in this row space, let's call it A times 0, 1, 1 plus B times 1, 0, 1. Okay. So for example, so now what we want to know is the weight of this word. We want to know which coordinates are 0, which ones are not 0. So for example, how do you know if the third coordinate of u is 0? Well, the third coordinate is 0. Basically, if and only if a plus b is 0, right? That's the third coordinate. But what are we doing here? This a plus b equals 0 is saying a times 1 plus b times 1, where this one and this one are exactly this one and this one. So really what we're saying is that the dot product of ab and 1, 1 is 0. So what we're saying is that if you take AB times 1, 1, which is V3, is 0. Okay. But when is the dot product of AB and V3 is equal to 0? Well, the points that have dot product with V3 equal to 0 are exactly the points on hyperplane 3. So this is exactly saying that AB is in hyperplane 3. Okay? And so what this is saying is that the weight of the word u is basically the number of non-zero coordinates, which is the number of hyperplanes that you are not on. So this is n minus the number of hyperplanes that you're on. So these are the hyperplanes that AB is on. And having said that, we can just do this computation. We can say the weight of u is n minus the number of hyperplanes of, let's call it A. Where A is what I called A comma B there. Okay. If I do this, then I can factor a z to the n out. And I get, now as u varies over big U, my vector A varies over FQ to the n. And then I get z to the minus the number of hyperplanes. So 1 over z to the number of hyperplanes of A. Okay. But what is this? Summation over all the points in your vector space of something to the number of hyperplanes. This is exactly what we got from this finite field method that I talked about last time. And so this is exactly z to the n times one over z to the n minus r times this other polynomial that I talked about last time. This co-boundary polynomial that is some polynomial that depends on the top polynomial. And I gave you the recipe to compute this polynomial at something comma something equals some function of the top polynomial. And if you plug in that, you're going to get exactly this result. Okay. So in other words, this theorem about linear codes is basically not basically, it is equivalent to the theorem that I mentioned last time about top polynomials of hyperplane arrangements. It's the theorem of Green in the 70s. Okay. And so this theorem tells us that a lot of the things that you want to compute for linear codes are obtained immediately from the top polynomial. Okay. And now let me show you an application of this. So people call this one of the most powerful theorems in coding theory. It's a very powerful theorem. And it says this. It's called the MacWilliams theorem. This is a pretty cool story, actually. So Florence MacWilliams was getting her PhD at the same time as her daughter. So they were classmates in the PhD program at Harvard. And so this was the mother's theorem. A really nice theorem. It says this. It says if you have U is linear code, of dimension k, let's say, then, again, a linear code is just a subspace, and so you can consider the orthogonal complement. Which is going to have dimension n minus k. So this is called the dual code. Okay. Now, a priori, there might not be any relationship between these two codes. And for example, you should notice that if n is 100, so you have words that are 100 long, and let's say that k is 95, okay, so that means you have a 95-dimensional space in fq to the 100. This has 100 to the 95 words. So this is 10 to the 190. A huge code. And this is telling you if you want to compute this by hand, you could just never do it because there's 10 to the 190 words, and you can't, for each one of them, figure out how many, what the weight of each word is. It's not reasonable. This is a much smaller code because this is a 95-dimensional space. This is a 5-dimensional space. Actually, why am I saying 100 here? This doesn't make any sense.
You said it
A 95-dimensional space has q to the 95 words. So even if q is 2 to the 95 is monstrous.
Yeah.
But if n is 100, so I said n is 100, k is 95, and so n minus k is 5. So this is a 5-dimensional space. So it only has q to the 5 words. So if q is 2, this is only 32 words, and you could do it by hand. Or at least ask your computer to do it. It's not a problem. And so it seems like this should be much more complicated than this, and this is impossibly difficult. This is simple. But what MacWilliams found is that actually these two are very, very closely related to each other. She found that if you want to compute the weight enumerator of the huge one, so I guess really I meant to do it the other way. I meant this guy to be very small, and you have a handle on it, and I meant this one to be very big, and you don't have a handle on it. But what MacWilliams says is if you can have a handle on the small code, that immediately tells you what it is for the big code. If you want the weight enumerator of this guy, it is just given by some function of the dual.
Wait, didn't.
And this. So this is saying if you can compute the weight enumerator for the small guy, you immediately have it for the big guy. Okay.
When we say last time though, you can just flip the guys.
Right. So, you know, when she proved this theorem, it was incredibly mysterious.
Yeah.
It's just kind of a magic thing. But now that we know that this is just an evaluation of the Tutte polynomial, then this should come as no surprise to us because, you know, the proof just says if U has matroid M, then the orthogonal subspace has matroid M star, the dual. And this is just saying matroid duality behaves well under Tutte polynomials.
So people didn't know
But this is the new proof. I mean, this is not how she proved
When
it.
did that? When was that?
That probably was proved in this paper of Green. When Green realized that that this was a Tutte polynomial, then he
Or
could
in
figure
general,
out.
I mean, when did people figure out that thing that you can flip the dual? Flip.
Oh,
the
people knew this as soon as they defined the Tutte polynomial.
Okay.
They defined it in a way that it behaves nicely
Okay.
under duality. But this is why people think of this as a very powerful theorem because it lets you build a simple code by hand and immediately get a huge one and a very powerful one. Okay? So they can use this to build new codes in this way. All right, stop there.
Federico, do you have a paper from 1965 called Transversals and Matroid Partitions by Edmonds and Fulkerson? Have you ever heard of that? I can't find it. Transversals and Matroid Partitions? I couldn't get it through our library. It's old. I don't know.
You can probably get them too.
Yeah, I can request it. I just thought I would ask you if you had a copy of it.
decreasing function 啊嘛。
啊，我問係嗰啲